For the last few years, the AI world has pretty much been in an arms race, a kind of digital space race where the entire mission has been focused on one thing and one thing only. Scale. It's all about more data, more compute, and, above all, more and more parameters. The whole philosophy has basically been, if we just make these transformer models big enough, they'll be able to do anything. But now, a small research lab from Singapore called Sapient Intelligence is questioning that entire premise with something radically different.
Instead of billions or even trillions of parameters, their model, they call it the Hierarchical Reasoning Model, or HRM, has just 27 million. I mean, to put that into perspective, that is tiny. It's about 20 times smaller than some of the models it's competing with. And yet, it's making these absolutely enormous claims about a skill that even the biggest models really struggle with: deep logical reasoning.
And that's exactly it, Julia. This isn't just a new model. It's a direct challenge to that whole bigger is better way of thinking. The question this paper really forces all of us to ask is, can a smarter, more brain-inspired architecture actually beat sheer brute force scale? Or is this all just hype?
That really is the million-dollar question. So here's our game plan for today. We're going to start by looking at the transformer's blind spot, like why do we even need a new approach in the first place? Then we'll dive deep into HMM's brain-inspired architecture, unpack its super clever training methods, and of course scrutinize those controversial results. And finally, we'll ask what this all means for the future of AI reasoning.
Okay, Yassine, let's start at the very beginning. I mean, the transformer architecture is king for a reason. It's incredibly powerful. So why do we even need an alternative? What's the fundamental problem here that HRM is even trying to solve?
Well, the paper makes this really interesting argument that for all their power, transformers are paradoxically shallow. And this all comes down to a concept called computational depth. Okay, so think about it like this. You're solving a Sudoku puzzle. You can't just solve it by looking at the whole grid at once. You have to take a series of logical steps, right? If this square is a 7, then that one can't be a 7, which means this other square must be a 7. Every single step depends on the one before it. A transformer processes everything in a fixed number of parallel layers. So if your chain of logic needs more steps than the model has layers, well, it just hits a wall. It literally cannot think any deeper.
Right, and the big workaround we've all been using for this is chain of thought, where you basically just prompt the model to think out loud. But as this chart shows, and as the paper argues, that's really more of a crutch than a real solution. It's forcing the reasoning to happen outside the model in text, which is slow and super brittle. I mean, one wrong step in that chain and the whole thing can just completely unravel.
Exactly. So this is HRM's radical idea. They want to move that reasoning scratchpad from the outside text back inside the model itself. They call it latent reasoning, letting all that computation happen in the model's internal hidden state. It's totally inspired by how our brains work, right? We can hold a really long chain of thought without having to narrate every single little step to ourselves in language.
Okay, a latent scratchpad inside the model. I love that idea, but it also sounds, super abstract. So how does this thing actually work? What does this brain-inspired architecture really look like under the hood?
Absolutely. So this is where it gets really cool. The core innovation of HRM is this two-module system, which is explicitly inspired by the kind of hierarchical and multi-timescale processing we see in the brain. You can totally think of it like Daniel Kahneman's thinking fast and slow. You've got a low-level module, which is the worker. It's updating at every single timestamp, handling all the fast, detailed, moment-to-moment stuff. And then you have a high-level module, the strategist. This one operates on a much, much slower timescale, and it's in charge of the abstract planning and setting the overall goals.
And it's the dance between these two modules that's so important. The process works in cycles, just like this slide outlines. First, the fast worker module iterates really quickly, say 12 times, just crunching on the details based on the current strategy. Then it settles into a stable state, a process they call hierarchical convergence. And only then does the slow strategist module do a single update. It looks at the result and plans the next big move. This whole loop allows the model to build up this incredible computational depth over time, letting it think for longer without its internal state just exploding into chaos.
When you say recurrent loops, my brain immediately goes to classic recurrent neural networks, or RNNs. But the key difference here, and what makes this so powerful, is that the actual building blocks aren't those simple old RNN cells. They're full-on transformer encoder blocks. So it's like they're getting the best of both worlds. You get the deep iterative reasoning of a recurrent system, but with the raw power of self-attention at every single step.
Okay, that architecture actually makes a lot of sense. But wait, anyone who's ever tried to build a recurrent model knows they can be an absolute nightmare to train. If you have these super deep loops, How on earth do you get a stable learning signal all the way back through those steps without the whole thing just blowing up?
Ha! You've hit on the million-dollar question. That's the biggest headache. The standard way you train these things is called backpropagation through time, or BPT. The problem is, it's insanely memory-intensive. To figure out the updates, you have to store a complete history of every single intermediate state the model was in. So for a long reasoning process with, say, t time steps, your memory cost grows linearly with t. Not only is that computationally a beast, but it's also not at all how the brain works. The brain almost certainly does not do BPT.
Right, so to sidestep that whole mess, the HRM team uses a BPT-free approach that's inspired by something called deep equilibrium models. It's a really clever mathematical trick, a one-step gradient approximation. Basically, instead of unrolling that entire history of thought, it calculates an approximate learning signal based only on the final stable state of a cycle. And the implication of that is huge. The memory cost for training stays constant, 0.1, no matter how many thinking steps the model takes. It's just a massive gain in efficiency.
Okay, so that trick solves the memory problem. But that wasn't the only thing they did, was it? The paper talks about two other big training innovations right here. Correct. The first one is deep supervision. So what they do is they break the whole reasoning process into segments. After each segment, the model has to make a guess, and it gets immediate feedback. It's kind of like a teacher checking your work every few minutes instead of just waiting for the final exam. This gives it a much more stable learning signal. And the second one, which I think is really cool, is adaptive computation time. They actually train a tiny reinforcement learning agent that just watches the model think. After each segment, it makes a decision. Do we halt and give the answer now, or do we continue thinking for another round? This lets the model spend more computational energy on hard problems and save it on the easy ones.
So we've got a really clever architecture and some seriously innovative training methods. But all of that is just theory. What really got everybody talking were the results. And some of them were, well, they were explosive.
Oh, absolutely jaw-dropping. They created these custom benchmarks, Sudoku Extreme and Maze Hard, which were specifically designed to knead these long, flawless chains of reasoning, and the results were just staggering. Really powerful, state-of-the-art models using chain of thought scored a perfect 0. They just completely failed. Meanwhile, HRM, this tiny thing with just 27 million parameters, trained on only 1,000 examples, achieved nearly perfect accuracy. I mean, that's the kind of result that makes everyone in the field sit up and pay attention.
It definitely is. But you know how it goes. When you make claims that big, the scrutiny is going to be just as big. And the result that really put HRM on the map, its performance on the famous ARC-AGI benchmark, also kicked off a huge firestorm of controversy. The actual creators of ARC initially accused them of cheating, and the general feeling in the community was captured perfectly by this quote. This might technically obey the ARC rules, but definitely not the spirit. Okay, so let's get into the nitty-gritty of what people were pointing to. First, and this is the really big one, their training process used demonstration pairs from the evaluation set. That's a huge no-no in methodology. Second, they trained a unique, special token for each kind of puzzle, which basically told the model what puzzle it was solving before it even started. So when the ARC team reproduced the results without these problems, they found that while HRM still did better than a similar-sized transformer, the gap was less than 5%, not the massive leap they had originally claimed. It really just goes to show how easy it is to accidentally or, intentionally game a benchmark. And look, all of that is totally fair, and you have to know about the controversy. But I really think if we only focus on the benchmark scores, we risk missing the most profound parts of this work. We really have to look beyond the leaderboards here. And one of the most fascinating things they found in the paper has nothing to do with accuracy scores at all. They did this analysis where they basically looked inside the model's brain and measured the complexity of its internal representations. They call it effective dimensionality. And they found something incredible. Just like in our brains, where high-level reasoning areas in the cortex are more complex than low-level sensory areas, HRM's strategist module spontaneously developed a representational space that was 3 times more complex than the worker module. This wasn't programmed in, it just emerged during training as the most efficient way to solve the problems.
And that, to me, is the real story here. Let's just forget the controversial ARC score for a second. The fact that this tiny 27 million parameter model can learn how to solve incredibly complex Sudoku puzzles from only 1,000 examples, that's the real headline. It is a stunning display of data efficiency, and it's a direct challenge to the whole scale is all you need philosophy. It proves that a better, more principled architecture can be a real alternative to just throwing more data at a bigger box. Which brings us right back to our central question.
The hierarchical reasoning model, despite its flaws and the whole controversy, it presents this really compelling alternative for where AI could go next. It's a path that's less about brute force scale and more about embracing principles from the absolute best reasoning machine we know of, the human brain. So the question this paper really leaves us with is this: is the future of AI going to be about ever bigger models, or is it about a smarter design?